In this video, we'll configure the regions and meshes for our Overset setup. For more details, you can also read the STAR-CCM Plus user guide. It explains what Overset is, which models are used, and how STAR applies it. In Overset, you have a background mesh and a separate Overset region. Physics is solved in both regions, and they exchange data through an interface. That interface is not just a single line. It's a thin interface region where interpolation happens between the two regions. In the figures, it's usually shown as a narrow blue band. Inside that band, STAR interpolates variables between the background and Overset regions. So data moves between the interface, the background mesh, and the Overset region. Now let's create our regions. First, I select the background geometry. Then I right-click and choose to create an Overset region from the geometry. I tell STAR to create one region per part and one boundary per surface. And for now, I disable automatic interface creation. I'll create it manually. I click Apply and Close. Now under Regions, you should see two regions. One is the background region, and the other is the Overset geometry region. A nice thing about Overset is that you can assign physics in different ways. You can use one physics continuum for both regions or separate continua. STAR will interpolate variables and coupling between the regions for you. In our case, we only need one physics continuum. So I create a new continuum, choose Select Models, and set it up. For this example, I'm modeling water. I use a segregated flow solver, and I set the model to 3D. I assume constant density, so I choose constant density. For time, I set it to implicit unsteady. I'm not adding turbulence right now. You can add it later if you want. For a simple start, I choose laminar. I don't need the optional models at this stage. These models are enough for our first run. I click Close. Now the physics continuum is created. By default, both regions are assigned to this same physics continuum. Next, let's define the boundaries for the background region. I start with the background inlet boundary. I change it to a velocity inlet. For velocity specification, I switch it to components. Because I have multiple inlet faces, I want to define vector components. I set Vx equals 1 and Vi and Vz equals 0 for those inlet surfaces. Now I select the outlet boundary. I change it to a pressure outlet. And the symmetry boundary stays as a symmetry plane. Now let's open the boundaries for the Overset region. This is the Overset boundary, so I set its type to Overset. I also set the Overset symmetry boundary to symmetry plane. And the wall boundary stays as wall, because we want it to be a wall. Great. Regions and boundaries are defined. Next, we create the interface between the Overset and background meshes. I select both regions, right-click, and choose Create Interface. Then I pick the Overset interface option. STAR creates an interfaces folder and builds the required interfaces automatically. Perfect. Now we can move on to meshing. Next, we need to generate the mesh for the whole case. To control the mesh better, I set up separate mesh operations for each region. So I go to Mesh, then Automated Mesh. First, I create the automated mesh operation for the background region. I enable Surface Remesher. The geometry is simple, so defaults are fine. For the volume mesher, I keep the default trimmer settings for now. I don't need prism layers here, because we don't need wall layers yet. I click OK, and I rename it to Automated Mesh Background. Now I repeat the same process for the Overset region. For the Overset mesh, I again select Surface Remesher. The optional settings are still not needed, because the geometry is simple. Here I enable Prism Layer Mesher as well, then click OK. Now we can generate the first mesh and check its quality. I right-click Automated Mesh, Background, and click Execute. Then I execute the Overset mesh too. First I rename it properly. I right-click Automated Mesh, Overset, and click Execute. Now the meshes are created. Let's create a new mesh scene to inspect them. Here you can see the current mesh quality, and we can improve it. For the background, I adjust the default base size a little. And for the Overset region, I also change the base size for that area. Now let's rerun the mesh operations one more time. I execute the meshing again for both the background and the Overset region. This is the mesh we get now. It's not perfect yet, but it's acceptable. You'll see only a couple of prism layers on the body, but it's fine for now. For now, I won't use the refinement block we created earlier. Later we'll use it, and you'll see why it's important. Alright, mesh is generated. Now let's set the solver controls and stopping criteria. First, we go to stopping criteria. I set inner iterations to 5. That's enough pressure corrections for this case. I set the maximum physical time step to 5 seconds. I disable maximum steps, and I enable the stop file option. Now I go to the implicit unsteady solver settings. For now, I keep the time step at 0.001 seconds. Later, you can switch temporal discretization to second order for better accuracy. But for this stage, first order is fine and more stable. For production runs, you should move to second order. I keep it first order for now, and I leave the other defaults unchanged. Everything else is okay, so we can initialize. I click Initialize. The solution initializes with no errors. That means both meshes are acceptable, and the Overset setup is working. If the background mesh is too coarse, it may fail to cut the Overset geometry properly. Then you'll get an error. We can test that later if you want. Now let's create a derived part so we can visualize the flow. Right-click Derived Parts and create a plane section. I set the plane normal in the Z direction. The default origin is fine. It places the plane at the domain center. I don't add it to a displayer yet. I just create the plane section. Now I create a new scalar scene from the scenes folder. In the scene, I rename the scalar display to velocity. More precisely, I set it to velocity magnitude. Velocity magnitude. From parts, I select the plane section we just created. If the legend is blue, it means no field function is assigned yet. Click it and choose which scalar to display. I select velocity magnitude. I leave the auto min and max settings at their default values. Then I click OK to apply it. Now the scalar is set. I hide the outline to make the scene cleaner. I change the projection to parallel for a better view. And I set the view direction to +Z, looking down onto the plane. Now I can start the run and watch the flow develop. I click Run. I let it run for a bit, and you can watch the flow around the body. Give it some time to develop, then we'll come back and check the results. Okay, let's pause here and review. I let it run for several iterations so the solution becomes more stable. The residuals look very good. Now I open the scalar scene. I change the color map style to smooth fill for a cleaner look. Here you can already see where mesh quality affects the solution. If you enable the mesh display, the issue becomes very clear. You can see the background mesh, the overset mesh, and the interpolation region. The connection and interpolation zone is visible right here. If I zoom in, you can clearly see how coarse cells affect the local field. Even inside the overset area, a coarse background mesh can reduce accuracy. So we need to refine the background mesh in that region. I go back to the background mesh and create a custom control volume. For the control volume, I select the refinement part we created earlier. I enable both surface refinement and polyhedral mesh refinement. And I set the target size to absolute. Now I check the cell size we used in the overset region. In the overset region, the target size was 0.1 meters. So I set my custom size here to 0.1 meters as well. Now I execute the background mesh operation again. Because the run is mid-step, STAR shows an error at first. It tells you the current time step must be completed before remeshing. So I click OK, and I use step forward to finish the time step. Now you see the message that the step is complete. Then I right-click the mesh operation again and click Execute. I wait for the new background mesh to be generated. After remeshing, STAR automatically interpolates the solution to the new mesh. So your results are transferred without restarting. Now I click Run again and let the solution continue. If I zoom into the same region, you can see the coarse cells are gone. The mesh is finer, and the field variation is much smoother. One key rule in Overset is that the cell size ratio must be reasonable. Because the solution must interpolate cleanly between regions. Also, the transition through the interface should be gradual, not abrupt. Around the interface, cell size and aspect ratio should change smoothly. In other words, keep the transition slow and controlled. If I hide the mesh now, you can compare this to the earlier result. This is still a first run, but you can already see the improvement. Compared to our previous single region exercise, we now solve across two regions. We fully defined two regions, background and overset. Flow enters through the background inlet, then interpolates into the overset region. We solve around the body, then interpolate back into the background region. So up to here, we tested the overset setup and saw how it works. In the next part, we'll add motion to the case. Next, we'll add motion and move the overset region with the block. Thanks for staying with me to this point. I'll see you in the next video.